The notion of connectedness is not very easy to check in general. Thankfully, there is a stronger notion called path connectedness that is often much easier to check. And not only that, path connectedness, usually the spaces we consider, that is manifolds, are connectedness and path connectedness coincide for such spaces. So let's begin with the definition of path connectedness. It's not unintuitive, it's straightforward. The definition is as follows. Let X be a metric space. Let X be a metric space. We say X is path connected. X is path connected. Let me just remark that path connectedness is also referred to as arc-wise connectedness by some authors. We say X is path connected if for each pair X comma Y in X, we can find a continuous function gamma from 0 1 to X. So such functions are called paths. That is a continuous function from the closed interval 0 1 to X. Again, there is nothing special about 0 1. You could have taken any closed interval, it would have worked. So we can find a continuous function gamma from 0 1 to X such that gamma of 0 is equal to X and gamma of 1 equal to Y. In short, given any 2 points in the metric space X, we can find a continuous path that connects X and Y. So the terminology is very geometric and visual. Let's see an example. One example. In fact, I'll give you an entire class of examples. A set U subset of Rn is said to be convex. If whenever X comma Y is in U, then the line joining X and Y is fully contained in U. Rather, the line segment is a better way to describe it. The line segment joining X and Y is fully contained in U. So it's almost by definition that convex subsets of Rn are all path connected. It's straightforward, it just comes from the definition. Now to your heart's content, you can draw many convex subsets of Rn to see that there are plenty of examples of path connected sets. Now coming to the important fact that we need, the fact that path connected spaces are automatically connected, and this theorem is very easy to prove. It's in fact just one line theorem. Any path connected metric space X is connected, and the proof is literally just a line long proof. Suppose f from X to 0 1 is continuous. Suppose you take a continuous function from the space X to 0 1. Given X comma Y in X, we can find gamma from close 0 1 to X continuous such that gamma of 0 is X, gamma of 1 is Y. This is just the definition of path connectedness. Then all you do is compose FO gamma. So FO gamma from 0 1 to 0 1 is continuous. So on the right hand side, when I said 0 1, I mean the closed interval 0 1. On the left hand side I meant closed interval. On the right hand side it's just the set comprising the two elements 0 and 1. But because 0 1 is connected, we have FO gamma of 0 is equal to FO gamma of 1, which just means f of X equal to f of Y. So in other words, we have shown that the function f is constant. So this quickly disposes of the proof that any path connected metric space is connected. Now let's see some concrete scenarios where we are able to show connectedness of some complicated spaces by exploiting path connectedness. Example 1 is R2 minus Q2. That is, you take the plane and punch away all the points whose both coordinates are rational. Now if you just look at it, it looks like I don't know what to say, a piece of cloth sufficiently zoomed in. If you look at a piece of cloth that is sufficiently zoomed in, it will sort of look like R2 minus Q2. Now this intuition sort of suggests that it is a connected set, but there is no easy way to show it just from using the definition of connectedness or the equivalent properties of connectedness. But you can immediately show this by path connectedness. Now I will just sketch a geometric proof and leave it to you to check that this can be made mathematically precise. What you do is the following. In fact, what I'm going to do is I'm going to show that R2 minus C is connected where C is any countable set. It doesn't matter. There's nothing special about R2. About Q2 is any countable set. So the key fact is that we are removing only a countable set. That's the key. So what you do is you have this R2 and lots of points are punched out. Okay. Now take 2 points that you're interested in. You want to find a path in between them. What you do is you draw small circles around these 2 points. Okay. Once you have done that, observe that this circle has uncountably many points. Prove that. It's rather easy to show. A circle will have uncountably many points. Same is true of this circle, of course. That means if you consider the various rays starting from these points and passing through the circle, there will be uncountably many such rays. Similarly here, there will be uncountably many such rays starting from the 2 points. But we have removed a countable set. Just C is a countable set. That just means that from these uncountably many, if you consider these uncountably many rays, only a countable subcollection of them will contain points of C, right? Because C is countable and you have uncountably many rays. Now, elementary geometry will just show you that you will be able to find 2 rays that actually intersect. And these 2 rays will not contain a single point of C. Okay. And therefore we have found a path. In fact, we have found a path that comprises just 2 line segments that connects these 2 given points. So this is just an intuitive argument. I want you to make it precise that R2 minus Q2 is in fact path connectedness, is path connected. Okay. Example 2 is a nice one. It is to show that there can be connected sets which are not path connected. Okay, connected sets which are not path connected. Now in an earlier exercise, you would have shown that the graph of any continuous function is automatically connected. If you have not shown this, please do it now. Okay, now what you do is you consider the topologist sine curve. Again, this is a bad picture. This is this example, more than being an illustrative example in topology, has been an illustrative example of why my drawing skills are non-existent. Nevertheless, assume in your mind's eye that this is the topologist sine curve. Okay. So what I'm going to do is I'm going to consider just sine 1 by x from 0, 1 to r. Okay. I'm just going to consider sine 1 by x from open 0, 1 to r. Now the graph, that is just the set of all points x comma sine 1 by x such that x is coming from 0, 1. This graph is connected. This is connected. Please show this. Show that the graph is connected. Okay. So this graph which is lying in R2 of sine 1 by x is connected. What I'm going to do is I'm going to consider G closure. Again, we have shown that any set that's squeezed in between a connected set and its connected set's closure, they are all connected. In particular, the closure of a connected set is connected. So if you think for a while, you will notice that the closure of the graph of the topologist sine curve, the way we have defined it, is just this graph along with this vertical line segment from -1 to 1. That will be the closure. Okay. So the closure of the graph of the topologist sine curve, the way we have defined it, is just the graph of the topologist sine curve along with this vertical line segment on the y-axis from -1 to 1. Okay. Claim is that this G closure, this is not path connected. This is not path connected. Now this is sort of intuitively clear. If you start at a point somewhere on this axis, there is no way to jump to the graph. There is no continuous path that connects the points in this particular line segment to the graph of sine 1 by x. So that's the basic idea. Let's establish this that rigorously. How do you do that? Well, let's take suppose gamma from close 0 1 to G closure is such that gamma of 0 is the point 0 1, which is there on that vertical line segment, and gamma of 1 is the point on the topologist sine curve, which I'm going to just take. It really doesn't matter what point it is. I'm going to take, for instance, pi by 2 I will not take pi by 2 because at pi by 2 I don't know what value it is. So I will take 2 by pi comma 1, right? Sine pi by 2 is 1. So sine 1 by 2 by pi is sine pi by 2, which is 1. Okay. So suppose you can connect gamma, you can connect 0, 1 and 2 by pi 1 with a path. Okay. Now what I'm going to do is I'm going to write gamma as gamma 1 comma gamma 2, write it as two components. Okay. And by characterization of continuity into product spaces, both gamma 1 from 0 1 to R and gamma 2 from 0 1 to R, both are connected. Both are connected. Not connected, both are continuous. Both are continuous maps. Okay. Now what is happening is eventually gamma 1 is traversing all the way from 0 to 2 by pi. So it has to, this gamma 1 cannot be a constant mapping. So what I am going to show is that gamma 1 is actually identically 0, which leads to a contradiction. Okay. Now what I do is, since I am assuming gamma 1 is not constant, there exists, so this is the crux of the proof, and as a very good teacher I am going to leave the crux to you. There exists t greater than 0 such that gamma 1 restricted to t comma t plus delta, okay, is never constant no matter what delta greater than 0 you choose. Okay, and gamma 1 of t is 0. Okay, so please prove this claim. There is a t such that when you restrict gamma 1 to t comma t plus delta, it is never going to be constant no matter what delta greater than 0 you choose. Now this looks very complicated, but let me reassure you that it is not so difficult to show this. Essentially gamma 1 is traversing from 0 to 2 pi, so at some point it should start. It's just capturing the fact that gamma 1 should start moving. It cannot just sit there at 0 forever. It has to start. I'm calling the point where it starts t. Okay, there must exist a point. Again, another hint, try to prove this by contradiction. If there does not exist such a point, then show that gamma 1 has to be identically 0. Okay. Now, so this gamma 1 from t to t plus delta is never constant no matter what delta you choose. Now once we have gotten this t such a point where this curve gamma 1, not curve, this function gamma 1 is eventually starting and not just staying put, what you do is the following. by continuity, choose delta greater than 0 such that diameter of gamma 2, we forgot gamma 2, it is feeling a bit lonely, so look at the image of gamma 2 from t to t plus delta, choose this to be less than half. You can obviously do this by continuity. Gamma 2 is also a continuous function. But wait a second, something weird is happening. What did we do? A picture in this scenario is really going to be worth 1,000 words. What is happening is gamma 1, no matter what delta you choose, it's going to move, right? It's the image of gamma 2, image of gamma 1, not gamma 2, image of gamma 1 of t plus delta is going to be an interval. In fact, it's going to be a closed interval, and one endpoint of this interval is going to be 0, because we know that gamma 1 of t is 0. It's going to be a non-singleton interval, right? It's not going to be a singleton interval. Why is it not going to be a singleton interval? Because we chose this t as the point where gamma 1 finally starts moving, right? So image of gamma 1 t plus delta is going to be some interval of positive length, okay? Which means that if you look at gamma 1 comma gamma 2 have to be points on the graph of the topologist sine curve away from t equal to 0 whenever gamma 1 of t is not, sorry, away from gamma 1 of t equal to 0, we know that gamma 1 of t, gamma 2 of t is there in the graph, which we call G, if I believe, is there in the graph of the topologist sine curve, okay? But here is an issue. We are at an interval that is touching 0, an interval like this. We know that as you approach 0, the topologist sine curve starts oscillating rapidly, okay? So this fact that diameter of gamma 2 t comma t plus delta being less than half, this is untenable. This is not possible. This is not possible. The graph, the diameter of gamma 2 t comma t plus delta being less than half is simply not possible if gamma 1 is going to take values here. So this contradiction shows that you could not have found a path gamma starting from 0, 1 and ending at 2 by pi 1. There was nothing special about the second point. There's a way to rewrite this proof in an obvious way which does not involve a proof by contradiction. Just show that any path that starts at 0, 1 has to be constant. That's also a good proof. Okay, so here is another example where we see path connectedness playing a role, but path connectedness is a stronger condition than connectedness. There are sets that are connected but not path connected. Thankfully, in the most interesting scenario, both coincide. Of course, I said it's true for manifolds, but we haven't defined what a manifold is yet. So theorem, if any open subset U of Rn is connected if and only if it is path connected. If and only if it's path connected. Proof. Okay, one direction is true in general. Path connectedness always implies connectedness. So all you have to show is connected implies path connected. Okay. And the technique I'm going to use for this particular proof, it might seem very obvious and straightforward once you understand it. But let me tell you that this technique that I'm going to use is going to be used throughout mathematics. Whenever you want to show something about path connected spaces, this is the technique that you're going to use. Okay. What we are going to do is, we are going to show that any two points in U can be connected by a polygonal path. What's a polygonal path? Well, it's a path which comprises of line segments. It's just a finite union of line segments. Okay, I'm not going to make it precise, but you can do so using partitions. Essentially what will happen is you can partition 0, 1 in such a way that on each interval determined by the partition, the image is just a line segment. Okay. Now what I'm going to do is I'm going to define this auxiliary set, which is typically called E. This is the set of points y in U. So first I'll write fix x in U. Look at the collection of all points y in U such that x and y can be connected by a polygonal path. Okay, and what I'm going to show is I'm going to show E is both open and closed. Okay, so I hope you got the basic idea. Since the set U is assumed to be connected, the only closed and open sets are going to be only closed and open subsets of a connected set are U itself and the empty set, but E cannot be the empty set. That's what we are going to argue. So first of all, X is in E. This is obvious. So E is non-empty. Okay. Second of all, E is open. Why is E open? Well, because let's just draw a picture and I will leave the rigorous details to you. It's rather obvious. Suppose Y is there in E. Suppose this point, just choose a ball, or in this case, yeah, just choose a ball centered at this point Y. Then obviously if you can join X and Y by some polygonal path, you can join every path in every point in this ball also by a polygonal path. Just travel to X from X to Y by this polygonal path and then just join one more line segment to it. Okay, so the E is open is left to you. Okay, I mean essentially just make this argument precise. Now we will show E is closed. That's the last part. And to show that, we will show U set minus E is open. And that is also equally easy, because if Y is in U minus E, and again you take a ball BYR which is fully contained in U, then BYR is contained in U minus E, for otherwise by the exact same argument we can connect X to Y by a polygonal path. Remember, we started out with a point Y which is not there in this set E. What I'm claiming is if U minus E is not open, then you can find some ball BYR which is fully contained in U. If this BYR is not fully contained in U minus E, that means there's some point Z in BYR from which you can connect. X and Z can be connected by a polygonal path. Just add another line segment, you will be able to connect X and Y. Okay, so this shows that both E and U minus E are open, which just shows E is open and closed. But because U is connected, this forces E equal to U. That just shows that any point can be connected to this given point X by a polygonal path, right? So that means given any two points, you could have applied this argument to any two points and shown that they both will be connected by a polygonal path. Okay, so this proves the theorem. For open subsets of the Euclidean space, connectedness and path connectedness coincide. This is a course on real analysis, and you have just watched the video on path connectedness.